Okay, hello everybody, we're back in the lab, back with Mr. C Science Teacher, and today we're looking at electromagnetic induction. Okay, so your objectives here, okay, they seem to mention this word EMF a lot. We'll check back at the objectives at the end. Okay, so flip lesson, so remember you need to do all three stages of the flip lesson, don't skip anything out, and make sure you spend some time thinking about a good question. Okay, first a little bit about EMF. Well, if you haven't guessed already, you're back in, I don't know, the late 80s here, so as an 80s child I had to put this in. It didn't get much better than that. Okay, so I'm not talking about EMF, the early 90s sort of not very good pop rock band. I'm thinking about something called electromotive force. Let's find out something.
150 years ago, Faraday discovered that moving a piece of wire through a magnetic field produced a voltage. If the wire is stationary, nothing happens. Move the wire from one pole to the other, and again nothing happens. Only when the wire moves up and down is a voltage produced. It's all to do with cutting lines of force. The wire needs to cut through the field lines before a voltage is induced. Following a line of the magnetic field has no effect. The results are the same if the magnet moves instead of the wire. A changing magnetic field induces a voltage, and an electric current flows. This is known as electromagnetic induction, and is the main method used for generating electricity.
Okay, so what we see there is that whenever a wire cuts through a magnetic field, a voltage is induced. I've used the term EMF, which means the electromotive force, it pushes the current around the wire. But whichever way you choose to use, voltage or EMF, we're inducing this in the wire whenever the wire cuts through magnetic field lines. And you can move the magnet or you can move the coils of wire. As long as field lines are cut, it won't matter. I'll show you in just a second. So here we go. Using our own big magnet. Here we go. In the lab. Okay, so down here you can see I've got the big magnet. This meter up here, if you see the needle twitch, it means I've induced some voltage. It measures voltage. Now, if I move that wire, you can just see a tiny movement. If I double over the wire, like this, you'll see more movement. Okay. Now, as another example, moving across, here I've got a coil with, I can choose either 125 or 500 coils of wire. I'll go for 125 and plug it in. It's a much smaller magnet, but if I move the magnet through there, we can see the needle moving. If I go for 500 coils of wire, you can see I'm inducing a lot more EMF, a bigger voltage, because I've got more coils of wire. So you can increase the EMF by using more coils of wire or a faster movement. Okay, there's another way you can do it, which is a bit more efficient.
To generate electricity, you need three things: a magnet, a coil of wire, and movement. Turn the magnet, and the needle rises, and you're producing electricity.
The movement of a magnet near a coil of wire generates an electric current. This simple action is all you need. Keep the magnet moving and you'll have a constant supply of electricity.
Okay, so one way to do it is to spin the magnet. Here's my example. Okay, what I have here is a coil of wire that I wound around a little cardboard tube, and on the inside are two magnets that I took from a flower arrangement. You can see me turning them around there. Now if I attach a little LED to that, if I spin that, you can just about, I hope, see flashes of light. There we go. Flashes of light whenever I spin them. So because I'm moving the magnetic field lines, we get some current induced by the EMF from the electromagnetic induction. Okay. Moving one step further, we go to this. Okay, so here I have a dynamo. This bottle-shaped thing here is a simple generator, and it's connected up to this light bulb at the end. If I spin the dynamo with this handle here, you can start to see the light bulb lights up. So one way to get a fast movement of the magnet is to spin the magnet. That's what the dynamo does. So here we are on, for example, a bicycle. Okay, now this is how it works. 1, 2, 3, 4. Okay, now obviously that's all well and good, but it doesn't make much electricity. Obviously, if you want to have all the things that you've got on your home that run electricity, you need bigger magnets and faster movement. Here we go.
Here at Drax Power Station, they generate a huge amount of electricity. They use big coils of wire and massive magnets. This is the generator. Inside is a magnet which is as long as a bus, and it's spinning 3,000 times every minute.
And surrounding the magnet are hundreds of coils of wire.
Okay, so you can see the huge size of the dynamo here. This is a generator, and it has hundreds of coils of wire and a massive magnet inside, which, as he says, is as big as a bus. So that's how you make a real generator. Okay, finally, you may recognise this. If you're lucky, you might have seen one of these. This fella here is Michael Faraday. Now, he said, the induced EMF is proportional to the rate of change of magnetic flux. In A level, we'd say this, okay? EMF equals N times by the change of flux per unit time. So that's the number of field lines cut per second. So he used this word flux rather than field lines. Well, that's the end of the summary. Thanks very much for watching the video today. Okay, check your objectives. Make sure you can reach higher on the level ladder. Remember, there's 3 steps, so now you've got to write your own words learning summary, okay, and come up with a question of what you want to learn next. And finally, remember, your own words learning summary is how you're going to be wise. I don't want to know what you've learned, so about the subject that you've learned, I want to know some specific examples of what you've learned. That's all, folks. Thanks very much.